Sam is an author, and he's also a reporter for Science Magazine. He went to school in Minnesota, where he studied physics and chemistry. But not to worry, this isn't a physicist trying to tell you about the chemistry in the periodic table. In fact, Sam went on to get a master's degree in library science. But as a student, as he'll probably tell you, he's fascinated by mercury, used to play with mercury, used to collect mercury from broken thermometers, so he had a real way to kind of do his own experiments. Maybe you'll tell us about some of those experiments. But this book, The Disappearing Spoon, made a big hit in 2010. It was a New York Times bestseller. It was the Amazon rated it as one of the top 10 science books of 2010. The Royal Society nominated it as one of its best books of 2010, science books. And he was acknowledged by the National Association of Science Writers as a runner-up as the best young science writer in the United States. An audio book is now available too. He's been featured on NPR, All Things Considered, and I have to tell you, he has a tantalizing website as well, with a lot of little gadget things on the periodic table. A periodic table puzzle, for example, sort of like a map of the United States. You can sort of put the states together. Well, in this case, you can put the periodic table together. It's good for kids. Videos focused on different stories of the periodic table, little cartoons and things like that. It's pretty interesting. Something for your kids to play with when they get tired of the Christmas presents this year. The book itself, I've read it. I bought it last year when Sam gave a talk at the Washington Academy of Sciences, a meeting of the Academy. And I have to tell you, the one thing I liked the most about the book is that he takes the story, the history, and the adventure of the discovery of the elements and makes that a bridge to the real world and a bridge to new science. For example, I wouldn't have thought he would pick Bose-Einstein condensation as a path, but he did. He took, I think, rubidium, and he said, and here's how Bose-Einstein condensation works, and actually gave some explanations of what Bose-Einstein condensation means. Sodium, talked about laser cooling and trapping. Radioactivity, obviously, he talked about when he did uranium and barium. Cesium was a bridge to talk about atomic clocks. So there was a lot about NIST and MBS in the talk, and for that reason, I thought this might be a great talk for our special Christmas colloquium. So would you join me in welcoming Sam Kean?
There they are. Thank you. Hello, everyone. Thank you for coming out this morning. Thank you, Bill, for the introduction. So I had a bad go of things in about third grade or so. I came down with strep throat something like a dozen times that year. And each time I did, I had to stay home from school, of course. And my mother would come in where I was lying on the couch, and she would put one of those old-fashioned mercury thermometers, you can see the end of one here, under my tongue to take my temperature. And I admit I was a little clumsy as a kid, a little prone to talking to myself when people weren't around as well. So not infrequently, when she would leave the room, I would start talking, and the thermometer would fall out of my mouth onto our hardwood floor, and it would shatter. But I admit I was never too upset about that. In fact, I was kind of secretly excited whenever that happened because I loved watching the mercury come out of the end of the thermometer. There you can see a broken thermometer. This is the result. And so I was always kind of excited to see the mercury. It was like these little liquid ball bearings that went scattering over our floor all over the place. And my mother was very cool about the whole thing. She never panicked. She never evacuated the house or anything like that. she would actually get down on her hands and knees with a toothpick, and she would brush the little spheres of mercury toward each other. And my favorite part was when she had two very near each other, and she would give them one final nudge, and then they would jump together into this slightly bigger sphere. And what fascinated me was that it was perfectly seamless. You couldn't see where there had been two balls before. There was just one remaining. And I just thought it was the most fascinating substance I'd ever seen, this liquid metal, so shiny and gorgeous. And we actually accumulated a fair amount of mercury over the years. My mother had this little pill jar she kept on a knick-knack shelf in our kitchen. And every once in a while, she'd get it around and whisk it around the lid so we kids could see it. And so when we were introduced to the periodic table, maybe even that same year, third grade in school, the first thing I wanted to find on there was mercury. And so I looked, and I couldn't find it. It just wasn't on there. And I thought, boy, that's weird. I thought mercury would be an element. I thought for sure. And of course, it was on there. But the symbol for it was Hg. And I thought, boy, that's weird. Neither of those letters are actually in the word mercury. Why is it called Hg? And so I looked into it a little more and found that the name comes from some Greek words and then through Latin. And so I looked into it a little deeper, and I realized that the element mercury has an association with a god of theirs from Greek and Roman times. And they also associated mercury with a planet. And so I looked into it a little more and tried to find more references and more places where mercury would pop up. And I found it through all sorts of science history. Scientists have used it for centuries. Alchemists were also obsessed with mercury. And then I started to find mercury popping up in some unusual places. In colonial history, people were shipping galleons with mercury in it over to the New World to help them with gold and silver mining. And I even found one kind of strange connection to American history, one of my favorite parts of American history. I'm from the Midwest. I'm from South Dakota. So we always had a very long Lewis and Clark section in our local history class. But I found kind of a strange story connected to Lewis and Clark and mercury through this man right here. His name was Dr. Benjamin Rush. He was one of the founding fathers of the country. He signed the Declaration of Independence. He was a physician who lived in Philadelphia, and he was best known for staying behind in Philadelphia during a yellow fever epidemic that struck there in the 1790s. It was very brave of him, actually. A lot of physicians sort of fled the place, and he stayed behind and cared for a lot of people. Unfortunately, Dr. Rush's favorite treatment for pretty much anything was a sort of mercury chloride sludge that he would feed people, often until their hair started falling out, their teeth would get loose. It really did a lot of damage, unfortunately. The idea in medicine at the time was that if you had an ugly ailment, you had to kind of fight it with something equally ugly, kind of fighting fire with fire. But anyway, Dr. Rush went on to get a patent on his medicine. He called them Dr. Rush's bilious pills. Each was about 4 times the size of an aspirin. They were very large pills. And there's really no delicate way to put what these pills were for. They were extremely powerful laxatives. They called them thunderclappers. And the idea was, the reason he packed 600 of these pills off with Lewis and Clark through the wilderness, the idea was that if they ate something that they shouldn't have, or they drank some questionable water that didn't agree with them, they could take one of his bilious pills and it would basically flush them out. It would clean their entire system out very quickly. But it also had kind of an unusual side effect for archaeologists and historians today, because they can actually now pinpoint a few places where they know Lewis and Clark must have stayed because the level of mercury in the soil is just too high for it to have been natural. So then from this one element, from just mercury, I learned some strange history. I learned about word origins and etymology. I learned about alchemy, mythology, poison forensics, a little archaeology. I learned so many different things from just this one element. And that's really why I wrote the book, The Disappearing Spoon, was because I wanted to get all of those stories into one place and kind of dig into the periodic table and find some of those hidden stories there. Because I knew there were whole swaths of the periodic table that we just never got to talk about in chemistry class. They were a complete blank to me, many of the elements on the table. And I also knew there were some really great stories out there about elements that everyone thought they knew very well, but that had kind of an unusual and hidden backstory to them. And one of those elements that did have an unusual backstory is the element aluminum. We're all familiar, of course, with aluminum today in pop cans and Little League baseball bats, things like that. But for a long time, in the 1800s, aluminum was actually the most precious metal on Earth. It was worth far more than silver was. It was worth far more than gold was. And the reason why is that even though aluminum is very common in the Earth's crust, it's the most common metal in the Earth's crust, it's almost always bonded to something else very tightly, usually to oxygen in some form. So it was very hard to get a pure sample of aluminum for early chemists. And when they started to get the first pure samples, very small amounts, it was considered sort of a miraculous metal. It was very light and very strong, but also had this nice sheen to it. It was very attractive. And pretty soon it became something of a status symbol for monarchs and emperors to get their hands on samples of aluminum. Right here you're looking at a centerpiece that was made for the Emperor Napoleon III. That's aluminum on top and that is gold beneath it. The French also had these sort of Fort Knox-like bars of aluminum that they would display next to their crown jewels when they wanted to show off. And Napoleon III also had this prized set of aluminum cutlery that he reserved for his most favored guests at banquets. And the lesser nobility were actually reduced to eating with gold knives and forks. And even the United States got into the game a little bit. This is the Washington Monument, and you can see right there at the top, that is a 6-inch pyramid of aluminum that they put on the very tip at the very top of the Washington Monument. And they did that for a couple reasons. One, they needed a lightning rod. There's not a whole lot else down there to catch the lightning, so they needed a metal of some sort. But the reason they chose aluminum over other metals was that the U.S. was kind of bragging a little bit at the time in the 1880s. And we were saying we're such an up-and-coming industrial power that we can afford to put aluminum of all metals on our public monuments. And of course, not long after aluminum went onto the top of the Washington Monument, the aluminum market crashed completely. And the reason why it did so was an American chemist and a couple of European chemists who finally figured out how to produce aluminum on an industrial scale and to get a lot of it produced at once. The American chemist, very famous, name was Charles Hall. He was working in Ohio when he figured this out. And he eventually founded what became Alcoa, the aluminum company of America. And probably not until the silicon semiconductor revolution about 80 years later did the demand for an element go up so much while the price for it plummeted just completely to the basement. When Hall opened Alcoa, he was shipping out about 50 pounds of aluminum per day. That was about all he could ship out, and that was plenty to meet the demand at the time. 2 decades later, he was shipping out 20,000 pounds of aluminum every single day. And during that time, the price of aluminum had gone from, dozens of dollars an ounce down to $0.25 a pound. So you can really see how the supply and demand went opposite directions there. And to me, I always think of aluminum as having sort of this classic narrative story arc. It had a very obscure beginning when not a lot of people knew about it. And then there was the rising action when emperors and kings were trying to get their hands on aluminum, and the U.S. was interested in putting it on their monuments. And then there was the climax, where Hall and the other chemists figured out that we can produce aluminum on an industrial scale. But even though that looked like a good thing for aluminum at first, it was kind of a complex twist of fate for it. because after that, at least the esteem of aluminum went into a pretty steep decline. And it went from being one of the more precious metals on Earth to a passé metal, but fairly productive. And I really think it depends on your temperament. You could look at it both ways, whether aluminum was better off as the world's most precious metal or as its most productive metal. It could go either way. And I really think it goes to show how the fortunes of the elements change over time, and how one generation's treasure can become something sort of passé for the next generation. So if I'd had to give a title to this talk, or a subtitle at least, I would have called it something like, Can the Periodic Table Tell a Story? Not, can the periodic table tell a story? But can the periodic table tell a story? No question mark. Because I always felt like it was obvious that it could. There were so many really great stories out there about all of the elements. You know, the periodic table is one thing, perhaps the only thing, that a lot of people remember from high school chemistry class. But if you really get into the stories on there, I really think that you can learn a lot more of the science than you might imagine just by telling and hearing those stories. It just happens to be how the human mind remembers information best, is in story form. And so when you get into those stories, I think they just sit with people a little better, and they get a little more comfortable with the idea of the periodic table and science in general. And again, the periodic table is one of the richer sources of stories out there. People eat and breathe the periodic table. They bet and lose huge sums of money on which elements will go up and down over time. Philosophers use it to probe the very meaning of science and the difference between physics and chemistry, things like that. It also poisons people, and it can help spawn wars too. And the first section I'm going to read tonight this morning, is about one of the elements that actually helped prolong a war. It's an element I admit I knew nothing about before I started writing the book. I definitely could not have pronounced it. But the element since then has become one of my favorite stories on the periodic table. It's the element molybdenum. Almost no one knows it, but the most remote battle of World War I took place not in Siberia or against Lawrence of Arabia, but at a molybdenum mine in the Rocky Mountains of Colorado. After its gas, Germany's most feared weapons during the war were its Big Berthas, a suite of super heavy siege guns that battered soldiers in the trenches of France and Belgium. The first Berthas, at 43 tons, had to be transported in pieces by tractors to a launch pad, and it took 200 men 6 hours to assemble it. The payoff was the ability to hurl a 16-inch, 2,200-pound shell 9 miles in just seconds. Still, a big flaw hobbled the Berthas. Lofting a 1-ton mass took whole kegs of gunpowder, which produced massive amounts of heat, which in turn scorched and warped the 20-foot steel barrels. After a few days of shooting, even if the Germans limited themselves to a few shots per hour, the gun itself was often shot. The famous Krupp Armament Company found a recipe for strengthening steel, however, spiking it with molybdenum. Molybdenum could withstand the excessive heat because it melts at about 4,800 degrees Fahrenheit, thousands of degrees hotter than iron, the main metal in steel. Doping steel with big molybdenum atoms also gummed up the iron atoms and helped prevented them from sliding around. The Germans were soon blazing away at the French and British with a second generation of Moly steel guns. But Germany soon faced another huge Bertha setback. It had no supply of molybdenum and risked running out. In fact, the only known supplier was a bankrupt, nearly abandoned mine on Bartlett Mountain in Colorado. Before World War I, a local had laid claim to Bartlett upon discovering veins of ore that looked like lead or tin. Those metals would have been worth at least a few cents per pound, but the useless molybdenum he found cost more to mine than it fetched. So he sold his mining rights to one Otis Kean, a feisty 5'5" banker from Nebraska. Always enterprising, King adopted a new extraction technique that no one had bothered to invent before. and quickly liberated 5,800 pounds of pure molybdenum, which more or less ruined him. Those nearly 3 tons exceeded the yearly world demand for molybdenum by 50%, which meant King hadn't just flooded the market, he drowned it. Noting at least the novelty of King's attempt, the U.S. government mentioned it in a mineralogical bulletin in 1915. Few noticed the bulletin, except for a behemoth international mining company based in Frankfurt, Germany, with a U.S. branch in New York. According to contemporary accounts, Metallgesellschaft had smelters, mines, refineries, and other, quote, tentacles all over the world. As soon as the company directors read about King's molybdenum, they mobilized and ordered their top man in Colorado, Max Schott, to seize Bartlett Mountain. Schott, a man described as having eyes penetrating to the point of hypnosis, sent in claim jumpers to set up stakes and harass King in court, a major drain on an already floundering mine. The more belligerent claim jumpers threatened the wives and children of miners and destroyed their camps during a winter in which the temperatures often dropped to 20 below. King hired a limping outlaw named Two Gun Adams for protection, but the German agents got to King anyway, mugging him with knives and pickaxes on a mountain pass and hurling him off a sheer cliff. Only a well-placed snowbank saved his neck. As a self-described tomboy bride of one miner put it in her memoirs, the Germans did everything short of downright slaughter to hinder the work of his company. King's gritty workers took to calling the unpronounceable metal they risked their lives to dig up, Molly be damned. King eventually sold the mining rights to Schott for a paltry $40,000 and started shipping the metal through underground channels to Germany. The U.S. government eventually caught on, and Metallgesellschaft admitted that, well, it just happened to be shipping all that molybdenum to their enemy. Sadly, though, those efforts came too late to disable Germany's Big Berthas. As late as 1918, Germany was using Molly steel guns to shell Paris from the astonishing distance of 75 miles. The only justice was that Schott's company went bankrupt after the armistice, when molybdenum prices bottomed out. King returned to mining and became a millionaire by convincing Henry Ford to use Molly steel in car engines. But Molly's days in warfare were over. By the time World War II rolled around, molybdenum had been superseded in steel production by the element right below it on the periodic table, tungsten. And unfortunately, history sort of repeated itself during the next World War with the element right below it, tungsten. Once again, Germany needed to strengthen their steel, and they found out that putting tungsten was even better than putting molybdenum in the steel because tungsten has an even higher melting temperature. But again, they didn't have any native source of tungsten, so they started to get shipments of it from wherever they could. And it just so happened that Portugal had lots and lots of tungsten. And Portugal was supposedly neutral during World War II, but they were shipping hundreds and hundreds of tons of it into Germany through underground channels across France mostly. So these two elements, molybdenum and tungsten, went a long way in explaining why Germany was able to hang on as long as they did during both of the world wars. And of course, after World War II ended, the Cold War descended on the US and Europe. And the Cold War actually so permeated our society that in some small way, the periodic table became kind of a new theater for the Cold War. It became sort of a proxy fight over the periodic table. And this story has to do with a couple scientists at the University of California at Berkeley, especially the scientist in the middle there, very famous, name is Glenn Seaborg. So remember that name, Glenn Seaborg. And these scientists were working they started off working in the 1940s, 1950s, trying to create new elements on the periodic table. And this was a very prestigious area of science at the time, still is, but back then especially was very prestigious because they were working with really basic science. And until then, until about the 1940s, the greatest science in the world was going on in Europe. The US had always been pretty good, but really the top scientists at the time were all in Europe. And if you really wanted to be a top scientist, you almost had to go over there and spend some time in Europe. It was almost required of you. But US scientists were gamely trying to do their own work, trying to find new elements, trying to create them, but they never quite could do as good a job as the European scientists. How many people here today have lived in or maybe from Alabama? One, okay. What about Illinois? Okay, a few more. How about Virginia? Okay, a few. Well, all three of those states should have had elements named after them. There should have been alabamine, there should have been alinium, and there should have been virginium. US scientists discovered these, tried to name them after their home state or where they were working, submitted them to journals, and the European scientists got a hold of the work and looked at it, and they said, no, we don't think you actually found these elements. Nice try. And so they rejected the claims for them. Then the European scientists turned around and they discovered them and named them things like francium so that they could get credit for these elements. So it was kind of a disappointment to a lot of US scientists that they weren't able to name elements after places. They weren't the ones discovering them. But this all changed with Glenn Seaborg and the group at University of California, Berkeley. They started to discover new elements, starting with neptunium, number 93, then plutonium, 94, then element 95, 96, 97, 98, 99, 101, 100, 101, and so on and so on. Box after box on the periodic table they were inking in. And again, there was a lot of pride that Americans were the ones doing this. This was the Cold War era. It was before and during the Sputnik crisis. And so we were very proud that we were able to show the world with this really fundamental science of the periodic table that we were the world leaders. But of course, there were teams across the world that were watching the Americans, trying to emulate them. There was one team in the Soviet Union, especially, that was working on this. But the Soviet Union team had a bit of an obstacle that the Americans did not have doing their work. And that obstacle was this man right here, Joseph Stalin. Stalin considered himself an expert on pretty much every single subject, all sciences included. He was especially good with the human sciences, psychology, economics, some biology, things like that. But he also considered himself an expert in the physical sciences as well, except he didn't like the turn that physical sciences had taken in the 20th century. He didn't like quantum mechanics, and he did not like relativity. They were both sort of spooky to him. They were kind of counterintuitive. And he didn't want good Soviet scientists working on quantum mechanics or relativity. So he was getting set to ban it in the Soviet Union and was actually going to ship any scientist who didn't renounce it off to the Gulag and basically let them die there. And he was getting ready to do this when a very brave advisor sort of raised his hand and pointed out that if Stalin did this, this might hurt the Soviet nuclear weapon program just a little bit if all the physicists were in the Gulag. And the nuclear science was really Stalin's kind of pet. He really liked it. He really wanted it. And so he thought about it for a moment, and he thought, yeah, you're probably right about that. And he made a very magnanimous announcement, and he said, leave the physicists in peace. We can always shoot them later. And so these were the kind of pressures that Soviet scientists were facing sort of on a day-to-day basis. And the work with the periodic table didn't escape that because, again, they were working with things like plutonium. But the Soviet scientists eventually figured out a way to sort of get around this. Joseph Stalin died eventually, thankfully for them. And they set up their own lab, started watching the Berkeley team, reading their papers. Meanwhile, the Berkeley team was making more elements. But then in the early 1960s, the Soviet team ended up beating the Americans to an element. And the Americans were not very happy about this. They did not take it very well. They got the Soviet team's paper, and they looked it over, looked at their methods, and then they went back to them and they said, no, we don't think you actually found this element. So basically they did to the Soviet team what the Europeans had been doing to the Americans for so long. And meanwhile, the Soviet team kept working. The Berkeley team found the element. They announced that they had it. And the Soviet team said, no, we don't think you found this element. Meanwhile, the Soviet team found another new element, and the Berkeley team said, no, we don't think you found it. And this kept going back and forth like this year after year. One team would find it, the other one would say no, but actually we discovered it while you were doing your sort of not very effectual experiment. And this kept going back and forth, and they were really disputing who had discovered these elements. And they kept fighting all through the 1960s, all through the 1970s, all through the 1980s, and then the Soviet Union collapsed, communism fell apart. But through the mid-1990s, they were still fighting about who had the rights to name these elements, over 30 years later in some cases. And what they were really fighting about, what they really, really wanted credit for, wasn't discovering as much as they wanted the right to name these elements. That's what's really important with the periodic table. You know, if you discover a new species of salamander or something, or some crater on the back of Mars, you get to name it, and you know, that's a very nice privilege for you. But it's not going to be hanging up in every single science classroom from now until the end of our civilization the way the periodic table is. It's really the most precious real estate in all of science. And that's why they wanted to get the rights to name these elements. And eventually, they couldn't sort this out, so they turned it over to a tribunal of international chemists, and they huddled, they talked about who was going to get the right to name the elements. And during this, the Americans had done something, submitted a name for an element that really made the rest of the world mad. They weren't very happy that the Americans had decided to name an element after a living person, after Glenn Seaborg. And it was supposed to be sort of like postage stamps. You had to wait till someone was dead for a few years and then name an element after them. But the Berkeley team said, no, the Seaborg was the most important scientist in this area that there's ever been, so we really want to name this element in honor of him. But the tribunal came back and they said, no, we're sorry, we can't let you do this. So the Americans said, fine, we're no longer recognize your authority. We're going to keep using the names we want to in the US and all of our journals and everything, and people will just have to get used to it. And this took the tribunal back a little bit, and they went back and huddled and talked about what was going to happen. And they came back to the Americans and said, okay, we buckle. They basically gave in to what the Americans had wanted. And you can see right here, that's a picture of a very aged Glenn Seaborg, and his finger is sort of pointing to element 106 down there, which is now and forever will be known as Seaborgium. And I just love this picture for a number of reasons. One, it's just a sweet picture. You can tell he's very happy about the whole thing. But also, it doesn't really betray how fraught the entire situation was and how much conflict went into getting to this point where they could name an element after a living person. And since then, they've officially changed the rules for naming elements. So he is the only person, and is the only person who will ever get to see his own name on the periodic table. So that's another reason why I think this is just such a fantastic picture. But another reason I wanted to write the book, in addition to these big stories about things like the Cold War and World Wars, was I really wanted to talk about a lot of the personalities on the periodic table, a lot of the scientists and other people who've contributed to the periodic table, either by discovering elements or contributing to its lore in some way. Marie Curie, very famous scientist, one of the only woman scientists of her era, discovered the properties of radioactive elements, really expanded the idea of what elements could be and how they behaved. But I also came across some stories about people that I really hadn't expected to with the periodic table, people like Mark Twain. Everyone knows him, of course, from his sort of laddish riverboat novels, but toward the end of his life, Twain started to dabble in what we might recognize as kind of science fiction-y type stories. And he even wrote one in the early 1900s about the periodic table, about two elements on the periodic table, radium and polonium. Marie Curie had just discovered these elements a few years before, and they really captured a lot of people's imaginations. But Twain took a bit of an unusual turn on them. The story is called Sold to Satan. It's about a metals speculator and what he does to try to win his soul back. But he really goes into some detail about how to get these elements and their properties and things like that. And it just sort of captured my imagination that someone like Mark Twain was so fascinated with these new elements that he felt the need to put them in a story and write about them. But the next section I'm going to read is about a scientist, someone who really had a big personality, but he's not very well known, even though I think he deserves to be, both for his personality and for the really fundamental work he did on some areas of the periodic table. He was a Hungarian scientist. His name was György Hevesi. And there's Mr. Hevesi. All right. In 1910, young György Hevesi arrived in England to study radioactivity. His university's lab director in Manchester, Ernest Rutherford, immediately assigned Hevesi the Herculean task of separating out radioactive atoms from non-radioactive atoms inside blocks of lead. And actually, it turned out to be not Herculean, but impossible. Rutherford had assumed the radioactive atoms known at the time as radium-D, were a unique substance. In fact, radium-D was just radioactive lead, and therefore it could not be separated chemically from the normal lead. Ignorant of this, Hevesi wasted 2 years tediously trying to tease lead and radium-D apart before finally giving up. Hevesi, a bald, droopy-cheeked, mustached aristocrat from Hungary, also faced domestic frustrations. Hevesi was far from home and used to savory Hungarian food, not the English cooking at his boarding house. After noticing patterns in the meals served there, Hevesi grew suspicious that, like a high school cafeteria recycling Monday's hamburgers into Tuesday's beef chili, his landlady's fresh daily meat was anything but. When confronted, she denied this, so Hevesi decided to seek proof. Miraculously, he'd achieved a breakthrough in lab around that time. He still couldn't separate the radium-D out, but he realized he could maybe flip that to his advantage. He'd begun using the possibility of injecting minute quantities of dissolved lead into a living creature, and then tracing the element's path. The creature would metabolize the radioactive and the non-radioactive atoms in the same way, and the radium-D would then emit little beacons of radioactivity as it moved throughout the body. If this worked, he could actually track molecules inside veins and organs, an unprecedented degree of resolution. Before he tried this on a living being, though, Hevesi decided to test his idea on the tissue of a non-living being, a test with an ulterior motive. He took too much meat at dinner one night, and when his landlady's back was turned, sprinkled hot powdered radioactive lead over it. She gathered his leftovers as normal, and the next day, Hevesi brought home a newfangled radiation detector from his lab buddy, Hans Geiger. Sure enough, when he waved it over that night's goulash, Geiger's counter went furious. Click, 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 click. Hevesi confronted his landlady with the evidence. But being a scientific romantic, Hevesi no doubt laid it on a little thick as he explained the mysteries of radioactivity. In fact, the landlady was so charmed to be caught so cleverly with the latest tools of science that she didn't even get mad. There's no historical record of whether she altered her menu, however. And I'm going to skip ahead a few pages in Hevesi's life. During the upcoming years, the 20s and 30s, he was traveling around Europe to a lot of different places, and he continued his work on what became known as chemical tracers, the radioactive elements that move throughout the body. This became very important work, the chemical tracers, still, of course, used in medicine today. And he kept getting nominated for the Nobel Prize for this work. But he kept losing out for various reasons, some of them not so good. And he was kind of disappointed that he kept losing out, but he kept soldiering on. Saddened but unbowed, Hevesi left Copenhagen for Germany again and continued his important experiments on chemical tracers. All the while, chemists such as Irene Joliette Curie, Marie Curie's daughter, repeatedly and futilely nominated him for a Nobel Prize. Annually unrewarded, Hevesi grew a little despondent. But the obvious injustice aroused sympathy for Hevesy, and the lack of a prize strangely bolstered his status in the international community. Nonetheless, with his Jewish ancestry, Hevesy soon faced direr problems than a lack of a Nobel Prize. He left Nazi Germany in the 1930s for Copenhagen and remained there through August 1940, when Nazi stormtroopers knocked on the front door of Niels Bohr's Institute, where he was working at the time. But when the hour called for it, Hevesy proved himself courageous. 2 Germans, one Jewish and the other a Jewish sympathizer and defender, had sent their gold Nobel Prize medals to Bohr for safekeeping in the 1930s, since the Nazis would likely plunder them if left in Germany. However, Hitler had made exporting gold a state crime, so the discovery of the medals in Denmark could lead to multiple executions. Hevesy suggested they bury the medals in the Institute's backyard, but Bohr thought that was a little obvious. So as Hevesy later recalled, while the invading forces marched in the streets of Copenhagen, I was busy dissolving the metals in liquid. To do this, he used aqua regia, a caustic mix of nitric and hydrochloric acids that fascinated alchemists because it dissolved royal metals, such as gold. When the Nazis ransacked Bohr's Institute, they scoured the building for loot or evidence of wrongdoing, but left the beaker of orange aqua regia untouched. Hevesy was forced to flee Stockholm in 1943, but when he returned to his battered laboratory after VE Day, he found the innocuous beaker undisturbed on a shelf. He precipitated out the gold, and the Swedish Academy later recast the medals for the scientists who'd sent them. Hevesy's only complaint about the whole ordeal was the day of lab work he missed while fleeing Copenhagen. And I'm happy to announce that shortly after that, Hevesy did end up winning the Nobel Prize and won it for the chemical tracer work. So the stunt with his landlady ended up paying off for him with a Nobel Prize. So a good lesson there. I'm going to wrap up tonight with a little bit of reflection on the periodic table itself. The Cold War story shows that there's been a lot of changes to the periodic table. I've had people come up and talk to me or send me an email saying that they hadn't looked at the periodic table in 30, 40, sometimes 50 years. And they were really surprised at the periodic table. It looked like it had changed shape, some of them remember. They were also surprised how many new elements were on the periodic table. And one thing people always want to know, they always ask me, is, well, are there more new elements out there to be discovered? Will scientists find more of them? And the answer is, well, kind of. Of course, scientists aren't going out in the world anymore and getting their fingernails dirty in nature trying to find these elements. They're actually creating them in laboratories. The newest new element added to the periodic table was element 117. The name is septium. That's Latin for 117. And that's just a provisional name until they can actually confirm that they discovered it. So there are new elements being added to the periodic table. But element 117 was sort of special in that it filled in a gap down there on the periodic table in the bottom row. Before that, it was just sort of this glaring hole. But when they got that element in there, it completed that last row. It sort of squared it off down there kind of nicely. And the rest of the elements on the periodic table were discovered in sort of a haphazard order, just wherever scientists happened to come across one. So it's really the first time that we've ever had a full and complete row on the periodic table like this. It's the first complete periodic table we've ever had right now. And it could be the only complete periodic table that we will ever have. Scientists are already, of course, working on making another new element. Next one might be 119, ununenium, or it could be 120. And when they do that, they'll, of course, have to put it on the bottom row and start over, start adding more. But the elements down there on the very bottom row are so fragile and fall apart so quickly that they might only get 5 or 6 atoms of those elements at once. And the only way they know that they exist is they have a computer readout somewhere that has some ones instead of zeros in certain places that tell them that they exist. The scientists might spend a decade, working on these elements, trying to create them, and then it can take a decade or more to confirm that these elements actually exist. They're that fragile and that rare. So it's kind of an open question whether we'll be able to get all the way across and complete a whole nother row of the periodic table. And some people think that we just won't be able to. The atoms just won't make it. So at that point, people want to know, well, is the periodic table kaput? Is it done at that point? And the answer again is, well, maybe, but maybe not. One thing I really enjoyed writing the book that I didn't expect to find out a lot about is that there are so many different arrangements of the periodic table out there. We're sort of used to our, sort of castles with turrets, look, with a little landing strip on the bottom here. But there are so many other arrangements. People have put in so many thousands of hours making new ones. There's a periodic table galaxy with the smaller elements in the center and the others sort of spiraling around it outside. There's periodic tables that look like board games. There's periodic tables with sort of a double helix motif going on. There are periodic tables that are mapped topologically onto taxi cabs and elephants and things like that. This is actually down at American Chemical Society in Washington, D.C. There are periodic tables that look like Moebius strips with this sort of part coming out in 3 dimensions and little twists there. There's a periodic table Rubik's Cube, where you can take the elements and you can turn them and put them in different arrangements. I'm not exactly sure what good that is to be able to do it, but a man holds a US patent on the periodic table Rubik's Cube. One of my favorite alternative periodic tables was a woman came up to me after a talk, and she admitted that she had gone to a photo booth at a fair or an arcade a few years before, one of the ones where you make a funny face in each picture. And she'd actually gone back something like 20 or 30 times, gotten lots and lots of pictures, different face in each one, and then she'd actually made a periodic table of herself. And she had put it on her fridge so that she could see herself as the periodic table every single morning. And I just thought, God bless you for doing something so strange like that. The periodic table means so much to people, and it means really different and unusual things to different people. And I really think the different arrangements of the periodic table show you, they help keep in mind something very important about the table. There's something universal about the periodic table, the arrangements and the relationships of the elements. But the way we actually put it down on paper is sort of contingent on what way we want to see it or what use we want to get out of it. And I really think that shows that the periodic table is still this amazing double thing. It's the basis of so much fundamental science. It's literally universal. But at the same time, it's a trove of stories, and it's really a reflection of all of our different passions and obsessions. And I'm constantly amazed at all the different things that we've been able to fit in there. So, thank you again for all coming out this morning.